Hi everyone. So today we are going to focus on the decision learning problem. Really the most essential step in understanding how intelligent agents interact with their environment to make optimal decisions over time. Okay, so what we are going to do is I'm going to start with this simple example. Okay, I hope you guys all right. And I'm going to call this the 1D cleaning robot. So now imagine we have a system and environment that where the agent robot moves along a straight line, and then we have different sections. So each section is a state, and the robot goal, the agent goal, is to navigate the 1D space and clean up efficiently. Okay, so this is the trash bin, trash can, and this is a charging station. So what I'm going to do is okay, let's call it 1D cleaning. I have a problem here. Cleaning robot. Okay, so I'm going to start by defining state. So state really represents more like the different positions here. So the charging station, I'm going to call it state 0, and this is state 1. The agent is currently in state 2, state 3, state 4, then state 5. Okay, I am also going to introduce actions. So the agent currently is in state 2, and it can move right, it can also move left. In state 3, if the agent was in state 3, it could also move right or left. Here, right or left. In state 1, it can also move right or left. Now, the charging station and this trash can state they are like the end of the operation. So we can call them the terminal state. So state 5 is actually a terminal state. State 0 is also a terminal state. And then the possible actions in terminal state, I mean the process has already ended. When the agent reaches those points, it can just stay there. There's nothing like move left or move right. I mean, at least for this simple example. And then what I'm going to do next is to introduce rewards. Okay, now I of course will go in depth into rewards later on, but think of rewards as they provide feedback based on the outcome of an action. So for instance, collecting trash might yield a positive reward. Maybe hitting an obstacle in a particular state or running out of battery might result in a penalty. So maybe in here, let's say properly disposing something might yield a positive 10, and maybe going back to a charging station might yield a positive 5. But we are going to see we're going to see this in depth later on. This is really just an introduction to rewards. All right, so this is our environment, and really as a programmer, you have the freedom to design it the way you want. Okay. All right, next, what I'm going to mention is that we can also define the problem as learning a policy. As learning a policy pi. Now, this pi takes in a state and then map that state to the best action. I mean, we can define the optimization problem we can define it as learning pi, this function. And of course, at the beginning, we don't know what pi is, but I mean, when you run the algorithm, or depending on the algorithm you use to learn the pi, at some point you're going to reach an optimal pi. You can reach an optimal pi. So at the beginning, the robot starts with no knowledge of the environment. It takes random actions initially and gradually refines the policy based on the rewards it receives. And then this iterative process of learning from feedback really forms the foundation of the field. So this is like more like the general algorithm. Okay, I am not sure if you can see because it is in blue, but then this is really what I have mentioned. At the beginning, it makes no assumption of the environment, starts with random actions, and then updates the policy based on feedback. Okay, now what I want to mention is that, of course, this is a simple example, but what we're going to do is, for the subsequent videos, I will gradually introduce even more complex environments. And then this is a cleaning robot, but then the field itself, reinforcement learning, it's not just for cleaning robots. It can be used in operations research, in robotics, of course, even in language and vision. So for instance, in operations research, it can be used to optimize complex systems like supply chains, transportation networks. So for instance, an airline might use these techniques to determine the most efficient way to schedule flights while minimizing delays and maximizing profits. Okay. All right. So really, this is just an introduction. But what we're going to do is, of course, we have framed the decision learning problem. In the next videos, we are going to model the environment mathematically. So we are going to see Markov chains to describe state transitions. State transitions here from maybe state 3 to 4. And we are going to see Markov reward processes to include rewards mathematically. We're going to see the Markov decision processes to incorporate actions and policies. And these concepts will lead us to the Bellman equation, which is the fundamental concept of the field. Okay. So, by the way, there's going to be a Jupyter notebook related to this this video that you can check out and play with. In fact, for the subsequent videos, most of them are going to have a corresponding Jupyter notebook. Okay, I hope that is clear. Let me know, please, if you have a question in the comment. I'll try my best to answer. Thank you.